other people joining you in your office or whatever, grab a coffee, and we'll be back. All right, well, welcome everyone to today's webinar entitled RCM Workflows to Create Custom Value-Added Products. I'm going to be your host for today, Kevin Jones here, and Jason is joining us. I'm not sure, Jason, if you can turn on your camera and say hello to everyone. So Jason's going to be giving a demonstration in a minute. But first, let's start off with some of the intro components. So as I mentioned, Kevin, myself here on the left, Director of Marketing for PCI Geomatics, and Jason Flatt, who is one of our technical solution specialists, is also on the webinar. I've also got Mauro, who's sitting behind me there. Mauro is ready to answer any questions, do any triage if you want to ask any questions throughout the session. Mauro's there to keep an eye on that, and myself and Jason as well have access to that throughout the session. So just real quickly, you are muted. So basically you'll see this little icon with a mute across your microphone. So that's normal. If you want us to unmute you, we can do that. We'll typically do that during the Q&A session towards the end. We encourage you to ask questions throughout the session. So if you see something that you're curious about, or if you have a question that you've been sort of wondering about and you want to ask it, just type it anytime. If we don't answer your questions live during the webinar, we'll be sure to circle back and send you an answer. This is a series of webinars. We've actually been presenting a series of topics since the fall, when the new version of our software came out towards the end of November. And what we did is we repeated some of those webinars starting in January. And you can see some of the topics there. We did, our most recent webinar was on Sentinel-1 Top. So the reason we mention these is they are, of course, available as a recording. So if you want to take a look, if there's a particular topic that's of interest to you there, you can definitely go take a look and watch those webinars. We will be publishing future webinars coming soon. We haven't quite picked our topic for March, but we'll be doing so very, very soon. Just on that topic, I want to thank each and every one of you that voted. We actually put together a poll and asked the radar community as far as we can reach into it. We posted on a LinkedIn SAR group that has about 3,500 people. We also sent some emails around locally to people that we know here in Ottawa that are in the SAR community. So thank you for helping us pick this topic. This is actually the #1 topic that people wanted us to present on, and so we've created this custom webinar based on that. So just a quick outline for today. So basically what we'll be doing is we're going to talk about the overview of the RADARSAT Constellation Mission. We're not going to go into lots of detail. We're just going to touch on a few things. We're going to explore the standard products that are delivered or that will be delivered through EODMS, which is the Canadian government service that is being used to deliver the data. And we're going to showcase an automated processing workflow that we've recently put together using simulated RCM data, and Jason's going to walk you through that. So just a few words about our company. PCI Geomatics has been in the remote sensing industry since 1982. We actually have, we have been delivering software for a long time, and we like to showcase our products as being a platform. So we have desktop software, we have high volume production software, And I'm just going to go through a few slides to explain that in a little bit more detail. Geomatica is our desktop software. Whoops. So Geomatica is our desktop tool. You can see some of the specific tools that form Geomatica. So we have our focus viewer in the middle, mosaic tool, and Ortho engine that are more for photogrammetric type tasks. And then of course we have Modeler and Python for automation. So it's a rich tool set that's been in development for many, many years, and it has I would say quite a lot of capability for synthetic aperture radar, which is what we'll be talking about today. We also have, of course, enterprise offering known as GXL. Here you see basically the login page for the GXL service or GXL system that's been installed. And you can see that it's a slightly different interface. It's a web-based interface. And what it does is it basically takes the functionality from Geomatica, those individual algorithms, and strings them together into automated workflows. And what you see on the right is what we call our job processing system, GPS administrator, where you can select specific jobs and automatically ingest data, process it, and you've got a few examples of some SAR specific jobs up on the screen there. Last but not least, we have, of course, the ability to deploy this technology, desktop or enterprise, to the cloud. Here's a piece of a cloud deployment schematic that we've used ourselves. So you can basically work locally. You can install Geomatica on a virtual machine or on a local machine, write Python scripts, build workflows. And then what you could do is you can Dockerize the software, Dockerize the script, point to the data, and then you can deploy that to an AWS cluster if you wish and scale it as needed. So really a nice flexible set of tools, both in terms of the capability for different types of systems, but also in terms of how it can be deployed desktop, enterprise, and cloud. Geomatica Banff is our latest release. So we released the software in November of 2019. So it's just been a few months. And some of the highlights included we added support for UAV processing. We added support for Sentinel-1 TOPS mode. And another key highlight that's part of our software right now is in preparation for the RADARSAT Constellation Mission. We actually have had technology in our software for many years. And of course, we've been testing that as we've been getting some sample RCM data from the Canadian government. Just a quick overview on our capabilities as it relates to SAR. As I mentioned, we have been developing technology for many, many years. You can see that Canada in specific has been an innovator in SAR for many, many years, since the early 1980s. If you're located in Ottawa and you're lucky enough, on some days you'll see the Convair out of the hangar. I think it's now housed at the Canadian Aviation Museum. So that is a key airborne radar system that was developed that was initially used for ice monitoring in Canada, then was replaced by RADARSAT 1. But a lot of the science and a lot of the innovation that happened in Canada was fueled by the Convair 580. So we were there at the beginning. We wrote some software to read the data and process the data and so on. If you sort of fast forward a little bit, RADARSAT 1, so you could see some of the graphics here, RadarSoft, and you actually see a picture of myself at the earlier part of my career in 1997 when RADARSAT 1 had just been launched. Basically PCI has been developing technology alongside the radar community in Canada and distributing that around the world for many, many years. We were part of some really important programs like GlobeSAR going back to the 1990s. And to this day, we continue to invest in SAR, and you can see Gabriel Gosselin, who's not going to join us today, but he's been part of our past webinars. And Gabriel is someone who studied radar and has developed a very strong expertise in SAR and polarimetric processing, and he's instructed some courses that we've given in Ottawa and so on. So we have a lot of expertise, and furthermore, we have some developers. I listed a few here. So John Wessels is one of our senior scientists who's been with PCI for many years. Wolfgang Luck is another scientist who has expertise with radar. and we have some developers who are dedicated to this as well. So we invest a lot. We really try to develop user-friendly tools. That's a key philosophy for us, is to make it easier for the radar community to work with radar data. All right. This is just a quick rundown on some of the SAR technology that has been developed over the years. You can see that we've been adding multiple SAR sensors over the years, including RCM, which has been updated, or actually has been available for many years, but now that we're getting real data, we're making sure that everything is functional. We've added complex data support, or updated the way that we support complex data. We, of course, provide you the ability to do georeferencing, orthorectification, and to work with RPCs from state vectors, which is important. Radargrammetry, or same-side stereo DM extraction from radar pairs, polarimetric processing, compact polarimetric processing, interferometry, and coming this year is some new capability that relates to terrain normalization and reprojection of optical data to slant range, which is moving towards analysis-ready data, which is a hot new topic in remote sensing in general. This is just a quick look at some of the highlights of how our SAR sensor support is unique. We have a single algorithm that allows you to ingest the radar imagery. It automatically parses key files. They range. They could be manifest.safe or product.xml or a specific format, depending on how the vendor distributes it. We preserve the data in the slant range, but we project it in ground range in the viewer, so it's easier to look at. And of course, you can work with the preferred calibration. You can work with intensity or sigma naught, gamma naught. It's up to you. You can display the data the way you want to. One nice thing is we make use of the state vectors for most sensors, at least the more modern sensors. And what that means is we can give you a precisely geocoded product without having to go through the orthorectification process. So right out of the box, reading the state vectors, the data will basically line up where it should within a pixel or two at the most. We provide you intuitive handling of complex data. We allow you to look at the amplitude and the coherence in the case of INSAR products and so on. We've got very specific ways of looking at the data in what we think users prefer. And of course, we carry a lot of the metadata through as we perform processing, from ingesting an image to co-registering it in the case of INSAR, to performing unwrapping an interferogram or filtering an interferogram. We carry all that metadata through as we're processing, which is important for understanding what's been done to the data. So just a quick overview of the RCM. So the RCM is Canada's newest generation of radar remote sensing satellites. So Canada has a long history, as I alluded to earlier, with going back to Convair 580, then RADARSAT 1, which was a C-band single polarized SAR, then RADARSAT 2, C-band quad pole, and now RCM, which is a constellation of 3 satellites that are identical, that are working to collect data on a much more frequent basis. So it's really exciting because there's going to be quite a lot of data being collected. You can see in this video, basically, oh, it's just playing here, it's just catching up. This is just a simulation or a visualization of the 3 RADARSAT satellites orbiting that are equally distributed. And so the revisit will be quite good, down to 4 days. So it's really exciting times for generating INSAR products on a much more regular basis and getting faster revisit. And it opens up a whole world of applications, which really makes automation more and more important, because the data volumes are going to be so much bigger than they were. We're talking, 10 to 20x from RADARSAT 2, if not more. It becomes really important to put in place automatic workflows to process the data. This is just a screenshot of the Earth Observation Data Management System. This is the way that you can actually download and access RCM products. You could see some of them are displayed here on the screen. This tool is available. You can browse a catalog, you can find out what images have been collected or what images will be collected. And you can see here that Jason has created an account, and you can access some images. At the moment, the RCM products are not fully being distributed. There are still a few things to do with Global Affairs Canada and the Canadian Space Agency to ensure that the proper application of the Remote Sensing Systems Act is respected. Only certain people, as we understand it, the Canadian Ice Service is primarily receiving data right now because they're obviously one of the biggest operational users. But for example, myself or Jason, we don't quite have access yet to get the data. However, the satellites were declared operational. I believe it was towards the end of December 19th. They passed the commissioning phase. The launch was on June 12th of 2019 from Vandenberg Air Force Base in California. So the system is collecting data, and the commissioning phase is over. So really looking forward to getting our hands on more data, as I'm sure a lot of you are here on this webinar. We thought we'd show you some examples of value-added products that could be automatically generated using Geomatica. We won't be producing these. However, it would be pretty straightforward to build workflows using Python or using automation to automatically generate these types of products. So orthos, mosaics, polarimetric discriminators, decompositions, similar to Freeman Decomposition from compact pole, coherence layers, coherent change detection, amplitude. So I'll just run through a few examples of that in a minute, but first I'll do the poll. So the first thing we'd like to know, we always like to engage with our audience and ask a few questions. So we're wondering, what software do you currently use for SAR processing and analysis? And there's no right or wrong answer. We're just curious to see what it is that you're using. And of course, the reason we ask this question is we want to make sure that we are giving you the best capability possible as compared to what's out there in the market. We are very much aware of what we're offering versus some of these other software packages, and we strive to always improve it. So I'm just going to wait a few more moments for that to come in. How's the poll going there, Mauro? Is it got mostly everyone submitting? Let's see. Okay, we got 60% voted, so I'm going to shut that down in just a few seconds here. So 3, 2, 1. So I'm going to close that down and share it out so people can see. It's kind of interesting. So a lot of you are using Geomatica, a lot of you are using Snap, a few of you using Gamma and other. So if you did put other, if you wouldn't mind typing in the questions panel and letting us know what that is. We know there's a lot of tools. There's, you know, MATLAB based, there's open source projects. There's a lot of things out there, and we're always curious to hear what's out there and what you're using and what we could do to make our tools even better. So back to the webinar. So just going to quickly go through a few value-added products for compact polarimetry. So I mentioned that we have the ability first and foremost to make orthos. Here I have just a RADARSAT 2 image over Vancouver, and you can see that when you look at the raw product and you overlay road vectors on top, there's a little bit of a misalignment. If I kind of go back and forth, you can see the roads here are not straight, and so we have the ability with Geomatica, obviously, to project that image correctly. We can do it either on the fly or we can generate a permanent ortho on disk. The benefit of doing it on the fly is you're looking at the data as if it were an ortho, which means you can overlay other data on top of it, but you're preserving the data in slant range and complex values and so on. So that's kind of a nice thing. And you can see when I overlay the vectors here that there's really like perfect alignment between the road vectors and the ortho. In this case, I made an ortho on disk. I didn't do a reproject on the fly or a state vector on the fly. But basically, we read the state vectors, we generate RPC, and then we load the data with the DM, and it's as if you're looking at an ortho on the fly. Another product that you would be familiar with if you've used Geomatica or know anything about us is we can, of course, stitch multiple images together. This is just a Google Earth showing Kenya, and going back to RADARSAT 1, actually, the Canadian Space Agency collected quite a bit of data over the whole African continent, and there was a contract where Geomatica was used to produce mosaics of the entire continent and of specific countries. So here you can see this is a low resolution view, but this data is available at 25 meters. So it would be, I believe, a wide beam mode or standard beam mode. And it would be made up of hundreds of individual images, which have all been mosaiced together. And again, that can be done automatically, orthorectification and mosaicing completely automatically using Geomatica. Polarimetric discriminator. So in the case of compact pole data or RCM data, we have the ability to produce this this type of polarimetric discriminator data. So here what you see is the alpha angle from a full quad data set from RADARSAT 2. And then what we did is we basically ran a algorithm to simulate a compact pole data set, and then we reconstructed a pseudo quad data and then generated that polarimetric discriminator alpha angle, same parameter. And you can see that the two products next to each other are very similar. But this is something, so we're showing this because up until now, we haven't really seen any RADARSAT or RCM data, but we're gonna get more and more data, which means you can go straight to the pseudo quad or the compact pole data products. So again, those algorithms are all set up to be run completely in an automated fashion. This is just another product that you might be familiar with if you've worked with RADARSAT 2. The Freeman Decomposition that leverages fully quad pole data has been adapted in our software. There's a specific algorithm called PSCompact Deck, and basically it gives you the dominant diffuse, specular, and double bounce scattering according to parameters that you're familiar with. So you can see the volume, the surface, and the double bounce showing up there. So these, again, are algorithms that are available in Geomatica that can be used to generate these products automatically. Coherence layers. So here we're in a different location now. We're in Monterey, California. So basically what you have is the ocean. You've got some golf courses, kind of the downtown over here. And keep an eye out on this runway because I'll be using this over the next few slides. But basically you have image 1, which is an SLC. So this will be the same thing for RCM. You'll be able to get the data as SLC. And then we have a second image, which is 24 days later. So I'll just kind of go back and forth. So you can see some intensity differences, some brightness changes. But because the data is collected in SLC, we can actually make use of the backscatter, which is the intensity, and also the phase. So how has the phase been affected by things that have occurred on the ground? And that's what this layer is. So the coherence layer is basically a byproduct of the INS raw, or the raw interferogram generation. And basically areas that are bright are highly coherent, or they haven't changed, whereas areas that are dark are very low in coherence, so they've changed quite a bit. And it kind of makes sense. The ocean is very incoherent, but if you keep an eye on the runway, the actual pavement is very coherent. But we'll zoom in a minute here and you'll see that there's been loss of coherence where there's some planes that are moving around on the runways and so on. Here's that example. So another thing that can be done automatically is we can derive a coherent change detection, or a CCD phase. So we can look at the change in the phase, and we can classify the change in the phase according to a percentile measurement. And here what we have is basically those two images, which I just showed. And you can see that this particular part of the airport has quite a few planes that come out of the hangars and are parked there probably overnight in between when they're being used and so on. And on the first image there, it looks like there's about 5 planes that are located there. And then on the second image, there's 4 that are gone, and there's a 5th left. And you can see that there has been change in the phase in the 95th percentile. So we can measure what areas have changed. We can delineate those areas. We can again do this completely in an automated way. We can do this using amplitude change detection in the case where we don't have SLC data. We're in the same location here. In this case, what we're looking at is SLC data, but if we were to have just detected imagery that's been ground range projected and is already orthorectified, we can still stack those one on top of another, and we can look at the change in intensity of the backscatter over time and make a very simple product like this 2-color multi-view, which I really like. Red has fled, blue is new. So you can see that this plane was there on the first day, and it had a pretty high backscatter, 5 dB. And then on the second day, it's minus 28 dB, so it's near the noise floor. So there's basically no backscatter response there. And the opposite would be true here. You'd have the minus 28 on the first image, and then 4 or 5 dB on the second image. So this is all possible as well. You can generate these types of products. We are not going to dive deep on compact polarimetry today. I'm going to skip through a few slides coming up, and then I'm going to hand over to Jason. We don't want to keep you here too long. We already have done a deep dive on compact pole. I was looking earlier today, and we have a great webinar that was presented with Gabrielle Gosselin and one of our senior technical solution specialists, Jean Bouffard, in June of 2018, and I've got a link to it there, and you'll be getting a copy of this deck, so you'll be able to go in and access that. It's a short presentation. It's about 1 hour, and Gabrielle explains everything there is to know about compact polarimetry in a short amount of time. We've also done training sessions on radar here in Ottawa and in other parts of the world as well, and that's obviously an option as well. But let's leave it at that. Just going to go through a few things here. Obviously, the main difference, just to quickly summarize, is with RADARSAT 2, we have 2 transmit, 2 receive, so we're able to make a full quad image. But in the case of RCM, in order to have a wide coverage and to be able to have less data coming through, because you're limited in terms of how many pulses you can send to the ground and how many you can record, just basic physics, with only 1 transmitter. Some sacrifices were made based on the user community, and the decision was made to have a single transmitter, which means that RCM only, the 3 satellites only have 1 transmitter. So what that means is you don't have full quad data, but technology exists within Geomatica and in other places as well, where you can reconstruct and simulate fully polarimetric data. So we have done a lot of work around this. We have a lot of tools, and Jason will be showing you how we can use some of those tools in a few situations. But the predominant mode is CTLR for RCM. There are other ways to represent the compact polarimetric data. RCM is choosing to distribute the products in CTLR. So you'll basically end up with, instead of 4 channels, you'll end up with 2 channels, which is right hand H and right hand V. So it roughly approximates like a dual pole image, if you will. These are some of the compact polarimetric tools. So PSCompact computes those different types of products. We actually have a tool that allows you to specify the transmit and receive configuration, so you can actually simulate different types of compact pole data. And then our big workhorses here are going to be PSCompDis. So basically this is the polarimetric discriminators, and this is the polarimetric decomposition, so DEC for decomposition. And Reconstruct basically allows you to simulate a full quad data set, so you can make you could take a compact pole and then make a pseudo quad. And if you're doing science and you want to compare information content from RCM as compared to RADARSAT 2, then you can do that using those tools. So I've already mentioned CTLR, circular transmit, linear receive. That's what that means. and that's the predominant mode for RCM, or the products will be distributed in CTLR. I'll quickly mention that the Freeman Decomposition gives you the double bounce, the volume, and the surface roughness. We already looked at an example of that. The Reconstruction Algorithm gives you the ability to take a quad pole or to simulate a quad pole, or pseudo quad. And here's a couple of examples. So this is a full quad pole data set over an area, and then we took our algorithm to simulate compact pole and then reconstruct a full quad pole data set, and that's what you see here is on the right. So and then some workflows. So these are the actual names of the algorithms in brackets. So you would start with a full quad data set in the case of RADARSAT 2, and you could do full polarimetric analysis. That's the RADARSAT 2 days. In the simulating compact pole data, you basically could start with a compact pole data set like a RADARSAT 2 data set, synthesize a compact pole data set using PSCompact, and then you could do polarimetric discriminators, or you could do the full quad data, do the simulated compact pole, and then do the reconstructed pseudo quad. So those are kind of some different, they're actually super easy to run. There's only a few parameters, file in, file out. There's not a lot of options. It's pretty straightforward to run these algorithms automatically. This is looking directly now in the future, or in the present, I guess, with RCM data. So you can start directly from a compact pole SLC data set, which will be distributed through EODMS. And then you can run the polarimetric discriminators and do your compact pole polarimetric analysis, or you can reconstruct the pseudo quad and do polarimetric analysis using the pseudo quad products. So I'm going to ask one more poll. I'm going to pass to Jason in a second. So our second question is related to what is your current main sort of bottleneck or the main challenge that you're having with processing. So current processing software is slow and difficult to use. Setting up automated processing chains for big data. You have difficulty interpreting results. Lack of flexibility to generate information from compact pole imagery, or something else. So if you have something else that you're struggling with, we'd love to hear about it. As I mentioned, we're trying to make our tools as user-friendly as possible. We know this is a difficult topic. As soon as we say polarimetry or compact polarimetry in the office, people kind of go, it gets a little bit intimidating, but hopefully we're providing you some tools that are easier to use and straightforward. So looks like only a few of you have voted so far, so I'm going to leave that open for just a few more seconds here while I grab a sip of water. All right. So I'm going to close that down in 3, 2, 1, and just share that out. So it looks like difficulty interpreting results is the key thing that people are having trouble with. So that's really interesting. It is a little bit challenging. So we'll keep working to put out some training material and tutorials to make sure that it's as straightforward as possible. So with that, I think I'm going to pass over to Jason now.
Hello, everyone. Thank you, Kevin. I'm just going to share my screen. Excellent. And just minimize that. Perfect. Hello, everyone, and welcome. As Kevin has mentioned, I'm going to go over the case study of coherent change detection. So just to give a brief overview, today I want to showcase just one example of generating a value-added product from RCM imagery. And as Kevin previously mentioned, one of the many strengths of RCM is its high temporal resolution. So as such, we can easily integrate compact pole data into PCI Geomatics standard INSAR workflows to perform multi-temporal coherence analysis. So for this case study, we extracted and filtered raw interferograms to identify areas of coherent change. Now, as we don't have actual RCM data, a stack of RCM data, we had to synthesize the compact pole imagery from RADARSAT 2 images. So we worked with 8 RADARSAT 2 scenes between May 3rd and October 18th, 24 days between each image, and the data was ingested and calibrated with a sigma knot. And this, of course, is also over the city of Ottawa. So just to go over the methodology and workflow that we utilized. So the first step was to ingest the raw RADARSAT 2 image scenes utilizing the SAR ingest tool. And once the images were ingested, we can then convert them or synthesize them into their compact pole data utilizing that PSCompact tool that Kevin made mention of. And that generated 2 channels, an RH and an RV. Following that process, we then ran the image co-registration, which was necessary to create our interferograms. And we utilized the first image, the May 3rd, as the reference image, and the preceding date as the dependent. And the output of that co-registry, the first co-registry, was the subsequent input as the reference for the next step. And so we just ensured that all the images in this temporal stack were properly aligned, utilizing the INS co-reg tool, because that's important for not just only the raw interferogram generation, but also for our coherence stacking and change detection analysis. So once we co-registered, we then generated our interferogram and creating RH complex channels. And what's important with that is we can then QA it utilizing the coherence and phase, which is written as a single channel, and intensity ranging from 0 to 1. And we'll look at how to visualize the data in focus in just a moment. Once we generated all the interferograms and their coherence layers, we then stacked them into a single file utilizing the data merge tool or transfer layer utility. And from that, we then utilized custom Python script to just run an absolute change detection or absolute sum of changes. Now, of course, this is just one example. Everyone else can have their own methodologies of analyzing the coherence change. And once we created the final output, we can then utilize the histogram visualization tool to identify the thresholds to see what pixels actually represent change, significant change to be more exact. And from that, we then utilize tools such as XPOL RAS to extract those areas of change, and then utilize vector or object-based features that we extracted utilizing our object-based object analyst tool for land cover and optical imagery, just to help identify the areas of change and give us some understanding of why that actually occurred. So what I want to quickly do, I'm just going to minimize that, is open up my workflow. And so we're going to go through these steps. So what we see here, I'm just going to go to RADARSAT 2, is our original RADARSAT 2 images. I'm just showing a subset. We worked with a lot more, but just for the interest of this webinar, I'm just showing 2. So we have our two RADARSAT 2 images. I could view the RGB mapper, so we can see they have their 4 channels, HH, HV, and so on. We then ran the PSCompact process to generate the compact pole data sets. So if we again view the RGB mapper, we can see that the RH and the RV channels were then created. From that, we then ran the INS co-reg, ensured the correct orientation, and then generated the raw interferograms. And so here's just a visualization of one. And so we're viewing right now as grayscale. We're viewing the amplitude, and that's also the coherence. So we can easily visualize the coherence either using the histogram tool. And we can actually see that there's minimum coherence. So it's a value between, of course, 0 and 1, closer to 1 means it's more coherent. So we could see that there's been there's not a lot of coherence between those dates, but that's okay because we're actually just measuring the coherence in total. But that's important to note because the dates are so far apart that many things, a number of things have changed that cause this dip in coherence. And so we can view, for instance, this two images right here. As we can see, a lot of change occurring. And of course, we can visualize the amplitude and phase and see the fringes. And even if we zoom down to this bottom right corner, we can just see quite a lot of things have occurred between the two different dates. So once we've generated all the raw interferograms, we now stack them all together. And Kevin made an interesting note. He said red fled and blue is new. That's something I just learned from him today as well. And what we can actually do with that is we can view the stack. And so here's the image of the stack. And I'm going to open up our RGB mapper again. And what's really interesting about this whole idea is that if we utilize the red channel as the date, that's the first date, and we utilize the green and the blue as the second date, everything that's red here is something that's changed. So these red areas have changed. And this is just another visualization tool for us to understand what kind of data we're working with and just to identify areas of change. So we can just go through this whole data set just to understand what's changing between the different dates. So once we have our stack, we can then perform the absolute sum of changes. And I'm just going to open that right here. And I'm just going to first zoom out to overview. We can just see it's a final output, and I'm going to just zoom into an area right here, for instance, and view the histogram. And what we can see is the histogram showcasing all the pixels, and we of course want to identify the pixels at the right end of the histogram, the end tail, or the tail end, because those are the ones that are actually going to showcase the most change. And this is all based on interpretation. Other people may have other methods for identifying different thresholds or visualizing the histogram, what values they could choose. But for just this purpose, we chose to identify pixel values that are greater than 14, just because we were looking more for potentially hard targets or moving targets, and we only wanted those pixels that contain high change in the coherence. So by identifying that value of 14, we can even visualize the histogram with the pseudocolor table, or the data with the pseudocolor table. So again, I'm going to zoom out. And I'm going to turn off the absolute sum and Pancro, but we can see it now in pseudocolor. I'm going to just showcase at the bottom left. I have a little table of contents of the colors, and so we can just see that what the colors are representing. And I'm going to zoom into this little urban area here, and we can just see those red areas are significant amount of coherence changes, and they also contain a bit of purple. So that's our whole range. We're trying to extract these kinds of features. And so we could run the XPOL-RAS tool. And an interesting thing about that tool, I'll open it up right now for everyone, is that the user can not only set the threshold minimum, but they can also set the minimum or maximum amount of area for these vectors. So this can help make sure that your vectors that you're creating have a minimum size, so you're not just getting teeny little vectors that are difficult to interpret. So that they can actually represent change. So once we ran the XPOL-RAS tool, I'm just again going to turn that off, turn that back on. We have all the little areas of change as red vectors, as we can see here. I then utilize these vectors to then clip out the pixel values of interest for this data from the pseudocolor image. And so we can just visualize these areas again, just related to the areas of interest. Now, what we can then do with this data set is then take that to our optical imagery and our land cover classification imagery, and just use that for analysis. So let's take that and bring it into our final area, which is the interpreted areas of change. And now, before I begin with this data set, I would like to just make it clear that I'm showcasing I have two optical images. One is Worldview 2 and the other is Sentinel. I'm just going to turn off the Sentinel so we can see. So the Worldview 2 doesn't fully cover the area of interest that we're working with, which is the area of processing. And also the dates are different. So I'm just using this as an example, but of course you want to make sure that any imagery you're working with was captured at a similar date. But this Worldview 2 data is old, and I'll show you some examples, and that's why we also have the Sentinel-2 imagery. So here's our area of interest in processing. I'm going to zoom to this area. I have a few areas of interest I'd like to bring our attention to. I then have the line cover classification, for instance, that can help us out as well. And I used Object Analyst to extract these features. And lastly, I have our objects of change as well as their colors. So we can zoom in, for instance, to the urban area, and we can see some significant areas of change over specific buildings. And that could be because the different types of roofs could be different times have water or different kinds of environment to the roof. I don't really know the best way to interpret that, but it would be either due to the roof or the environment. But that can just give us some information. In addition, if we look at the quarry over here, we can again see areas of coherence change, but they're in the water. And this is the problem with the data of the Worldview 2 data set. So I'm actually going to turn on the Sentinel-2, and we can see the water is far more reduced, and a few more. We can identify these areas of interest and potentially, or areas of change, and potentially this could be objects such as tractors or large vehicles that may have been moving around over this area. And lastly, I just want to bring our attention to this wetland. And we can see that there's, again, areas of coherence change, and that could lead to a number of questions as to why is that happening. So these are just a number of ways we can utilize compact pole imagery to extract information for analysis and interpretation. Actually, lastly, one thing to bring up to everyone's attention, we can also identify which pairs, which interferogram pairs contain or had the most impact on those pixels. So here's some examples of color coding the different pairs between the different interferograms, so we can see which dates had the most impact in our vectors. This can just, again, give us some more information in helping identify what we're looking at, what we're working with. And Kevin will bring you to the last poll.
Great, thanks, Jason. I'm just going to quickly ask another poll. It's actually relates to people like Jason who are available. So would you be interested to work with one of our pre-sale specialists? Jason is a technical solution specialist, and he's available to help you evaluate Geomatica. So if you want to send some data or identify some data that you're curious to work with, we actually have quite a few resources available internally, like Jason, to help you understand how to use the software. Perhaps if you're looking to use our software and you're using something else, you don't want to invest the time that it takes to learn how to use the tools. So basically, you could take a shortcut. You can use one of our staff members to evaluate the technology, and then you can set up a meeting and review with that. Or you could keep looking at the software on your own. Nothing wrong with that. Let us know if you have any questions. We have our support department. We have a lot of resources available for you to use. So I'm going to close that down, and I'm just going to wrap up. So next slide, Jason, you might as well keep driving there. And I'll turn my webcam back on so people can see me. So yeah, so we have, as I mentioned, quite a few resources available. We have a cookbook with some Python recipes, and we have our support destination website. We actually have an advanced SAR training course. About this time last year here in Ottawa, what we did is we gathered the radar, part of the radar, synthetic aperture radar community from Ottawa, and offered a course that lasted 4 days. And we actually recorded a lot of it using cameras and so on. And one of the days is available on Udemy, which is a self-learning platform that's freely available. You can Go to our YouTube channel. We have the raw videos from that whole training course available. We have specific tutorials available as well. This is just a picture from that training course. So a year ago, roughly today, I guess it was somewhere in the middle of February there. I can't remember when, but there's some of our people. You can spot Gabrielle in the back there with the sort of the blue across his shirt, and John Wessels on the back on the left, who was one of our instructors as well. And a number of people from the community, both Canadian government and some people from academia who participated in that. And we've since repeated the course in other places. I actually gave a very similar course in Poland, and we're about to give the course again this year in other locations. So if you're interested to attend one of those courses, you should definitely reach out to us, and we'll let you know where they're happening, and maybe you can attend them. So with that, I'm going to go to Q&A. One of the things, Jason, I'm going to ask you to drive again or keep driving. So if you can escape out of the PowerPoint, one of the questions that came up as you were giving your demo was maybe the starting point. We started with a whole series of results. And one of the questions that one of the viewers had was, how do you actually get data in the system? So maybe you can quickly show focus and show SAR ingest, or pop open a Python script that shows how to get imagery into our system.
Yes, we can easily use the SAR ingest tool to have our data ingested. That can be accessed in Python. I have a number of scripts I can just visualize. It will just take a few moments as my screen just seems to be misbehaving. I apologize for that. Oh, there we go. Yep. So let me go to
Sorry to put you on the spot there.
No worries.
We didn't prepare this part.
So here's just an example. I'm just going to hide that question panel. So this is easy. This is one way we can run our tools. I'm just going to show this. Is that I don't have the Python scripts immediately accessible, but I'm just going to do SAR ingest or SAR ingest. And this is just one of the tools that will ingest our data set.
Yeah, just for the benefit of the audience, I think Jason's going to the easiest thing to show, but if you open up Focus and you just browse the algorithm librarian, Jason, maybe that's easier.
Sure.
Oh, is it off the screen? Is that why? Okay, yeah, so just go Tools, Algorithm Librarian, and then go to SAR, I guess. So these are all the algorithms. There's over 550, there's probably more. And if you go to, for example, yeah, any one of those. So SAR ingest is the main algorithm that's used to bring the data in. So basically you can execute these one by one inside this environment. We call this our focus environment. Or you can write a Python script that calls that particular function silently. It's really up to you as a user to decide how you want to run it. There's a lot of different ways. But yeah, I guess the starting point, Jason, was SAR ingest, and then from there you did PSCompact, and then from there you did PSComDis and so on, right? That was kind of the workflow?
Correct, yes.
Yeah. So all the algorithms can be executed one by one, but typically what we do is we automate the production of the products based on a known workflow. So you can see this was the workflow that Jason highlighted for the coherent change detection, where we ran SAR ingest, PSCompact, INS co-reg, which aligns the data to each other, then the raw interferogram, and so on. Thanks for that. We had a question here. So we have a question about, is the patch, I'm assuming this is like a software patch, this question, is the software patch to support SLC information from RCM already out? So here's what I'm going to say about RCM support. We have had RCM support for quite some time. The issue that we've had is the ability to test our support with a full complement of data sets. So we did get some data from the Canadian Space Agency shortly after launch, and We performed a lot of QA, including SLC data, and we were successful in processing the data for SLC. However, there's some other modes which we hadn't quite added support for, and we're adding that in, and but we really need a full complement of data to be able to test everything. So should work, but really we won't be comfortable saying everything is perfect until we have had a chance to perform quality assurance across our technology with more full data stack. We have a question here about, is there a workflow to merge optical and SAR? So we didn't choose to highlight that today, but what I would say about merging optical and SAR is, if you're doing analytics, which I'm assuming that's where you're coming from, then probably the best thing to do is to perform image segmentation, either on an optical image or a radar image, which we support in our software, and then calculate statistics on those objects from both optical and SAR. And that's a way to fuse the data, if you will, where you're pulling multi-sensor information at object level and fuse the data. If you're talking about making images that fuse the backscatter and the multispectral content, yeah, we have tools for doing that, like intensity, hue, saturation, and so on, but I haven't seen people really use that operationally because it's not really a quantifiable data set that could be used to perform analysis. So we really focus on quantitative analysis and ease of use with our tools. Let's see.
Quick thing, actually, on that question, just to let you know, we have done a webinar utilizing SAR imagery for object analysts to extract wetland features, just as an example. So if that is kind of what you're looking for, it's on our YouTube channel, so take a look there if that is of what you're interested in.
For sure. We'll take one last question. So we had a question about coherent change detection and whether that was possible with Sentinel-1 data. So I answered that question earlier, but I'll just repeat it out loud here. So we do have the ability to perform coherent change detection on Sentinel-1 data. The beauty of our system is we try to process the data the same way for all the different sensors. So you run SAR ingest, whether it's RADARSAT 2 or PAL-SAR or RCM or Sentinel-1 or whatever data set it is, and then you can run other algorithms like the CCD phase algorithm if you're working with SLC data exactly the same way. So absolutely, that's possible. So we're just 2 minutes before the hour. I think I'd like to close it off here. I would encourage you to get in touch with us. Very easy. So it's last name at PCIgeomatics.com. So I'm Jones at PCIgeomatics.com. Jason is flat, F-L-A-T-T at PCIgeomatics.com. Be sure to reach out and let us know if you have any questions. Thanks for your time today. Appreciate having you with us. Take care.